All right, section 4.6 is our last section of material for the semester. And it is about integration still, right? And it's a specific type of integration called substitution. And specifically, you usually hear it referred to as U substitution, and you'll see why shortly. But I want to show you where it comes from, because it didn't just sort of appear out of nowhere. There's a reason for its development and use in the way that we're going to see it used. And we're going to talk about it from the perspective of taking derivatives. So let's say we had a function, y equals sine of x cubed minus 4x, and you were supposed to find its derivative. So what would its derivative be? What is y prime?
Cosine of x cubed minus 4x times 3x squared minus 4.
Okay, and so what property in general did you have to use in order to do that, Ben? That is a chain rule problem, right? So this is a chain rule, and we're going to consider going in reverse. That is, if we took the y prime that's created there, and we wanted to be able to go backwards and find out what y would have been, what inherent difficulties are there in doing that? Why does that look like it would be a challenging thing to do if you didn't know, hey, we got this by taking a derivative? What part of that y prime makes this look hard? Okay, I heard three things at the same time. One at a time. There's a cosine in it. Okay.
The last part.
The last part. What do you mean by the last part, Jason?
Well, because it looks like it's product.
It looks like it's a product rule. All right. That's actually what I want to hit on, okay? The fact that there is something that looks like a product, and not only is there a product, but it's a product where we can't sort of simplify it. We can't, like if this cosine weren't there, like Taylor said, and we could actually just multiply it out, that'd be great. But the fact that this looks like a product, it not only looks like it is a product, right? The fact that this is a product makes this very complicated if we were to try to sort of, with what you know already, be able to take the antiderivative of this. So there's a difficulty in doing this because it's a product. I mean, that's the issue here. So we want to figure out how we can deal with this in a different way. So one option when we're presented with finding antiderivatives that look like a product is to decide if there's a composite function. Composite function simply means a function that's inside of another one, right? Like things where we used chain rules when we were doing derivatives, something inside of another one, for which the inside function's derivative is one of the factors being multiplied. So if you go back over here to this problem, if you started out right here at y prime, the inside function, the function that looks like it's inside of something else, is this piece right here. It's inside of a cosine, right? So one of the things that we want to be able to identify is if the product that is going on in the problem, if that part that's circled in red, if its derivative is the piece on the outside. And of course it is here. I mean, like we created it to be that way. But we're going to see ones where we didn't create them to be that way, and they're still that way. Okay? So that's where this is coming from. This is coming from the idea that we look to see if something inside has its derivative being multiplied on the outside. All right, so considering y prime above, x cubed minus 4x is an inside function. Its derivative, 3x squared minus 4, is one of the factors being multiplied. All right, so when we recognize that in a function, whether we created it or not, I mean, as we move forward, what we're going to do is we're going to let the u be the inside function. So u equals x cubed minus 4x. Now, when we did implicit differentiation and we took derivatives, we didn't call them primes. We used this notation that looked something like dy dx. Do you guys remember that? Or dy dt, whatever the function was that we're taking the derivative with respect to. Well, here the function's name is u. I just created something that's called u equals. So I'm going to find du dx. That is, I want the derivative of x cubed minus 4x with respect to x. We've already done that. We did that as 3x squared minus 4. And then what you're going to see me do is you're going to actually see me write this dx on the other side. So in other words, du is equal to 3x squared minus 4 dx. This notation right here in the green box is the notation we're going to be using on each problem. So let me show you how it looks when we create one of these problems from scratch now. I showed you first all where every single piece came from. So if we were doing the antiderivative of the cosine of x cubed minus 4x times 3x squared minus 4 dx. If that's what we were finding the antiderivative of, we would do a step to the side that says u equals the inside function, x cubed minus 4x. We would write down du equals 3x squared minus 4dx. And I know this looks a little bit weird, that's why I wanted to show you where it came from. This comes from the du dx up here, with the dx multiplied to the other side. Okay? Why do I have it written like that? Well, I have it written like that because what I really want to do is I want to replace everything with x's with something with u's. So I've separated all the u's on one side and all the x's on the other side. Do you see that? So when you're going back into your function over here, if you see this piece right here in red, this is the same as this piece in red, right? And they're equal to du. So I can replace this piece with du. And then the part here in green and this part in green are identical, so they can be replaced with u. The script s at the beginning doesn't change. So this function, oops, I left something out. Sorry, I left out the cosine. That didn't go away. So I've got my integration symbol, my antiderivative symbol. The cosine did not get replaced in any of my substitutions, did it? This green x cubed minus 4x gets replaced with u. The red gets replaced with du, and we have something that we can find the antiderivative of very quickly, very cleanly. Most of you who've come into my office could do this pretty well because you've done so on your quizzes. Some of you still need to come into my office for your quizzes, don't you? Yes, please do. We'll talk about times for that later. All right, so what is the antiderivative of cosine of u? Sine of u. But we're not done because right now the problem is written in terms of u, and how did the problem start out? In terms of x. We need to put it back in the terms it started out in. Oh, we need a plus c here as well. Let's do that right now. So we need to replace the u with what u equals, and u equals x cubed minus 4x, and then plus the c. So this is the general antiderivative of the y prime that we created. And if you go back to the very top now of where we started, that's the same function with a plus c on the end, right?
What happened to the du?
du is a notation that goes away. It means with respect to you. The du and the script s at the beginning are connected. Remember?
So, yeah, du is just like dx.
du is just like dx. Exactly. Okay, any questions on where the pieces are coming from? We're going to practice more of them, but okay, let's see ones then starting out from the forward direction instead of going backwards like I did. All right, here's a function. We've got the cube root of 3 minus 4x squared times negative 8x dx. So as we're looking with this, what we want to do is we want to identify what looks like it's inside of something else. So what does it look like is inside of something else? The 3 minus 4x squared. Maybe I should use a color. Let's go with red. This looks like it's inside of something else. And in fact, this is where we would start. And if we make a mistake, we just try something different when we're done because we didn't pick something correctly. That happens sometimes. But this looks like it's inside of something else, 3 minus 4x squared. And then I take the derivative of u. So what's the derivative of 3 minus 4x squared? Negative 8x dx. Okay? That dx needs to be there. Why in the world is that helpful?
Because that gives us the...
You take because it matches the end.
Because it matches the end. That's why it's helpful. Is that negative 8x dx, it's going to show up in green here in a second, this negative 8x dx matches the part that's not got red around it, the negative 8x dx at the end. So we can actually plug some things in now. So this is equal to, the script s doesn't change, the cube root doesn't go away. What's going to be under the cube root now? U, because that's the piece that it's in red. And then what's going to go at the end? Du, because all of that at the end, negative 8x dx, is equal to du. Now that notation isn't especially helpful, but it would be more helpful to write it like this, right? All right, so now what is the antiderivative of u to the 1/3? U to the 4/3 over 4/3, and then plus c. So let's write that as 3/4. U to the 4/3 is the same thing as cube root. That's what that 3 in the denominator means, of u to the 4th plus the c. So since it started out in radical form, the answer needs to be in radical form. And then since it started out in x, the answer needs to be in x. So our last step then is to replace the u with 3 minus 4x squared. All of that is to the power of 4, and then plus c. What do you think?
So considering it's a cube root and
Mhm.
there's a power of 4 underneath,
You could rewrite it to pull it out. The problem with, I wouldn't say problem. The thing about doing that is that I don't know that it necessarily makes it look any simpler when you
Yeah.
write it that way. So if you're willing to leave it like this, that's okay.
okay.
I want you to simplify things, but I don't want you to make a bigger mess out of it when it simplifies, because sometimes that happens when you start simplifying as it becomes messier than it was before. This is okay. You can leave it like that. All right, this one's going to happen a little bit differently. This, first of all, doesn't really look like a product, does it? It doesn't. It's a quotient. But did you know that multiplication and division are really the same thing? I know, crazy, isn't it? They really are. They're just, when you multiply by something, you're dividing by the reciprocal. When you divide by something, you're multiplying by the reciprocal. They have this sort of a dual relationship. It's kind of like addition and subtraction. They're really the same thing, right? Subtraction is really just adding negatives. Somebody probably told you that. I remember in 7th grade, I had a teacher that said there's no such thing as subtraction, and we all looked at her like she thought she was just crazy, right? What's the deal? Because she was talking about adding negatives instead. So really, we have multiplication here, so it is appropriate for us to think about this in terms of U substitution, because it really is multiplication here, okay? So, that said, what looks like it's inside of something else? What would my inside function be?
1 plus x to the 4th.
Right, 1 plus x to the 4th. Then what's the derivative of this?
4x cubed dx.
All right. Now, there's a little problem with that. What's the little problem that developed here?
We don't have a 4.
We do not have a 4 in our problem, do we? No. But you know what? It's really easy to get 4s into a problem. I'll show you how you do it. So what you're going to do is you're going to just divide both sides by 4. And lo and behold, what we're saying is that x cubed dx is equal to 1/4 of du. So instead of the x cubed dx having the 4 in front of it, I do have an x cubed dx in my problem, right? It's right here. So the x cubed dx at the front here, at the top, and then on the side, will be replaced with not just du, but 1/4 of du. And it's most helpful, so I'm going to write it like this, to write the 1/4 out in front of the problem, and the du at the end. And then what actually ends up happening on top is that you just have a 1. So you basically are factoring that 1/4 out in front. I like to factor out constants in front because it helps me to remember that they don't change the problem's value. They just are part of the problem's solution. Okay? They're just 1/4 in front of the answer when I'm done. Now, the part underneath, then, is not going to have an x in it anymore either. It's going to be 1 plus x to the 4th, which is actually the u to the 2. And we'll do one more rewriting step before we actually take an antiderivative. How else could we write that would be more helpful? U to the negative 2. All right, then, 1/4 is part of the answer. What's the antiderivative of u to the negative 2? U to the negative 1 over negative 1, and then plus c. Now, if I simplify this, this becomes negative 1 over 4u plus c, right? The u to the negative 1 comes stacked down in the denominator. I just move the negative out in front. Of course, I don't have a u in my original problem, so what's my last step? Yeah, plug in u, back substitute. So my substitution value would be 1 plus x to the 4th plus c. If you want to distribute the 4th through the denominator here, you can. If you want to leave it in factored form, that's fine too. There's really not one that's simpler than the other. So I'm just going to leave mine like that. Any questions on that one? That was a little different.
You just lose the script S.
You don't lose it. You actually perform the operation. So this notation here is telling you to do something. It's like when you multiply, you lose the cross multiplication sign. You don't really lose it. It's because you actually did what it told you to do. This script S with the du, those two pieces tell you take the antiderivative. So this step right here where I actually took the antiderivative, the notation's not there anymore because I did what it told me to do. Yeah. The same thing happened when we did limits, right? Once we plugged the number in, the limit notation was allowed to disappear because we'd done that part of the operation. All right, let's try another one. This one's got trig in it. It actually looks similar to the one that I started with the whole lesson with, but it isn't quite the same. Similar though. All right, so on this one, what do we have? What would u be? X to the fourth. Now, it doesn't really look like there's something inside of something else. Sometimes it's difficult to see what should be the inside function. One of the things you can ask yourself if you're having trouble is, where would my calculator force there to be parentheses if I were putting this in? And if you did that on this one, your calculator would force parentheses to be around that x to the fourth. It actually would. I have one calculator that doesn't do that actually, but most calculators force there to be parentheses right there around the angle. So that is my inside function. Nicely enough, what is the derivative of x to the fourth? 4x cubed, which actually is the other piece of the problem, and then the dx is also necessary there, right? So the 4x cubed dx here at the problem, that gets replaced by du. The script s and the sign don't change, but the part that's in parentheses, x to the fourth, also gets replaced by u. So this problem looks an awful lot now like the one we started the whole lesson with. What's the antiderivative of sine of u du? Negative cosine of u plus c, right? So the negative's there, and I've got my cosine. And then what's the antiderivative, or I'm sorry, what's the value for u? X to the fourth, right? U is x to the fourth, so this is negative cosine of x to the fourth plus c. Is that good? Okay. There are so many things that you might want to try here. You might try some sort of simplification with changing this into cosine squared times cosine, and then sine over cosine's tangent. You might try something with that. There's lots of things to try, but let me suggest that when you see a sine and a cosine within the same problem, u substitution is often very helpful because they are each other's derivatives, right? That's a really nice feature to recognize. We never will choose something that has a denominator with a variable in it to be du. The denominator can't be a part of du, okay? Which means the denominator must be part of u itself. So if I let the u be something in the denominator, what would u need to be?
Cosine x.
Just cosine x. That's correct. Because then the du, what's the derivative of cosine? It is negative sine. You have to be really careful when you're working with these because you're doing derivatives in the middle of antiderivatives. I know some of you are not fond of that already. If you do end up taking Calc 2, I know many of you do have to take that, you're going to be doing more of that when you first start the class again too. This idea of doing derivatives in the middle of doing an antiderivative. I don't have the negative though in the problem, correct? So I'm just going to divide it or multiply it to the other side. So this is negative du equals sine x dx. So this piece right here will get replaced with the du at the end, the negative at the beginning, and the 1 on top. Cosine cubed x is what's in the denominator. So what's going to be my denominator now? U cubed. Cosine is u. Cosine is cubed, so u is now cubed. And more helpful would be for this to be written as u to the negative 3, right? Okay, the negative in the front still stays. What's the antiderivative of u to the negative third? U to the negative 2 over negative 2, right? We add 1 to that power. The negatives are going to cancel, so we might as well simplify that nicely. I need a plus c on the end as well. So this is actually 1 over u squared, 2u squared plus c. And then the problem started out with x's, so it needs to end with x's. So this is 1 over 2 cosine squared of x plus c. Or if you want to put the cosine in parentheses or the squared on the outside, that's okay too. We have this. Yes?
How did you know to do, like for the u, how did you know to do cosine?
Well, the problem is that if I let the u be cosine cubed, Then I've got a chain rule, so I'm going to have to bring a 3 down, rewrite cosine to a power of 2, and then take the sign over there. And I don't have all of that in my numerator. I only have sine in my numerator. So I want to simplify this so that the derivative that I take is a part of the problem. So when I take the derivative, it needs to be there. It can't have extra stuff. It could not have a constant as a multiplication factor, but that's the only thing it can be missing or have extra. And so that's how we would make that decision. Okay, the last two problems are a little bit different. What's a little bit different about 5 and 6? They're definite integrals. They have limits of integration of 1 and 9, right? Okay. I'm going to show you my favorite way to handle that, and then I'm going to tell you another way to handle that, because I know that not all of you will take your Calc 2 from me. In fact, most of you won't, because I'm not teaching it next semester. And so for those of you who are taking it maybe somewhere this summer or even next semester with Dr. Marsh, she may do something different, or that professor may do something a little bit different. I want you to be aware of the other option, okay? So the first way of handling those limits of integration, you're going to love it, you ready, is to ignore them. That sounds pretty good, right? I'll show you when we sort of think about them again. But the first thing we're going to do is we're going to do use substitution. Now this one looks weird, doesn't it? It really does look a little weird. But if you take a look or think about what the inside function would be, I think you're going to get the right inside function. The weird part's going to come next. So what's the inside function? Yeah, it's the part in parentheses, right? 1 plus the square root of x. And I'm going to write this that way, and then I'm going to write this as the x to the 1/2, which is how we'll take its derivative, excuse me. So this is u. Okay, so even if it looks weird, just do what you know to do, which is what looks like the inside function, and see where it leads you. So it's going to lead us correctly down the right track. What's the derivative of 1? 0. What's the derivative of x to the 1/2? Okay, that's good. Now, the 1/2 is fine. I'm going to leave the 1/2 as it is, as a multiplication. What do we do for x to the negative 1/2? What does that look like if we simplify it back to the original notation? 1 over the square root of x. Now, we don't have the 1/2, but we do have that square root of x in the denominator, don't we? We really do. It's a part of the original problem. And if you're not so certain, or you're a little bit leery about how it's written, remember that you can do this with fractions. You can separate them, oops, like so. So then this first piece, again, ignoring the 1/2 that I just have over here, which we'll deal with that in a minute, looks like this. And the second piece, 1 over the 1 plus, looks like it has to do with the u. Okay? That 1/2 we're going to deal with in exactly the same way that we dealt with some of the other ones. We're going to move it to the other side of the equation. So in order to get rid of the 1/2, I'm going to multiply both sides by 2. So I've got 2 du, and that equals 1 over the square root of x dx. So this piece and this piece are right here. They're going to be replaced with the 2 du. So the 2, I'm going to write it in front, and the du I'm going to write in back. So all the pieces in green got replaced with 2 du. The other piece then still has the 1 over. The 1 plus square root of x is u, so this is u squared. Is that okay? All right. So there's a 2 still here. I'm going to do my integral of u to the negative 2. Notice I've ignored the 1 and the 9 limits of integration, right? And by ignored, I mean literally, I mean they do not get written. In fact, they cannot be written when you've got the u's in the problem, because that 1 and that 9 are values for x. And when I turn the problem into u, I can't have that 1 and the 9 there because they don't apply to u. Okay? So this is one way to handle it. All right, so what's the antiderivative of u to the negative 2? And then I actually don't need a plus c on this problem. How come? Eventually I'm going to do what? I'm doing a definite integral. Eventually I'm going to put some numbers in. I'll show you where, but eventually we're going to have some numbers in, so we don't need a plus c on this one. All right, so this is actually then equal to 2 negative 2 over u. Does that look okay? And you know what u equals. We started the problem there. So this is actually negative 2 over 1 plus square root of x. Now that the problem is back in x's, we can plug in the 9 and the 1. Yes. So we've got things back in terms of x. I can evaluate negative 2 at 9 and 1. So I have negative 2 over 1 plus the square root of 9 minus negative 2 over 1 plus the square root of 1. Okay then, so what's the square root of 9?
3.
3 plus 1 is, so this is negative 2 over 4, which is negative 1/2. The minus a negative here, right? I've got a negative here and a negative here. Can be a plus. So I've got plus. I've got square root of 1, which is plus 1 is, and 2 over 2 is 1. So this is negative 1/2 plus 1, and what is negative 1/2 plus 1? It's 1/2. Okay? This is how I handle limits of integration when I use u substitution. I ignore them until the very end where I plug them back in. Let me briefly tell you how else you can handle them and why I don't like handling them that way. Okay? The other thing you can do is at the point when you change things into u substitution, you can change your limits of integration so that they apply to u instead of to x. Here's how that works. Up here originally, x was equal to 1 and 9, correct? So if x is equal to 1, we could put the 1 in here. 1 plus the square root of 1 is 2. So we could literally put a 2 down here in place where the x's have changed into u's. I could put a 2 down here. And then if I do the same thing with 9, I could do 1 plus the square root of 9, which would give me 3 plus 1 is 4. And I could put a 4 up here. So this would go from 2 to 4. The nice thing about that is that I never actually take anything and turn things back into x's because I've changed my limits of integration to apply to u, which means that at the point where I got to here, negative 2 over u, I would simply be plugging in the 2 and the 4. It's very clean. It's very nice. Here's the problem. If you do too many of them in that direction, you very well may forget that if you didn't have limits of integration involved, you would have had to change them back into x's. Do you see what I'm saying? I like being able to leave them in terms of x's because they more cleanly mirror the other process that we're doing when we don't have definite integrals. They mirror the other pieces a little bit better. So that's the way that I handle them. But not everybody does that. So I want you to be aware. All right, here's another one. This one has something interesting going on. Let's see if you can pick up on it. If you can't, it's okay. But take a look at it. Do you see anything interesting going on here?
Addition between sine and cosine.
There's addition between sine and cosine. That's true.
It's 2x.
What's that?
It's 2x and x.
One of the angles is x, and one of the angles is 2x. That's going to cause something interesting to happen. Exactly. We are going between 0 and pi. So because we're using the trig functions.
Well, if that 2 wasn't there, it'd be 1. Or no, it would be sine. It's not squared. So the 2 have to be married. There's no product.
There doesn't look like a product. That's definitely something interesting going on. It doesn't really look like there's a product, but it's sort of in this section being thrown in here like there's a product rule. So let me sort of show you what's going on. There's several of those things that you guys mentioned that cause us to have some sort of weirdness. Here's the first issue. Sine x, which is on the left side of the green mark that I've made. You know how to find an antiderivative, right? There's absolutely nothing about that that needs u substitution. Agreed? There's nothing. The other side, however, says cosine of 2x. Well, you don't have a formula for cosine of 2x unless you want to go dig out your double angle identities from trig. I don't think that's what you want to do. We can use u substitution with that one, and I'll show you how, but we don't need u substitution with the first one. Agreed? So we're going to split it into two different integrals. Exactly. So we're going to have one integral from 0 to pi of sine x dx, plus, and that one doesn't need u substitution, plus the integral from 0 to pi of cosine of 2x dx. And that one will use U substitution. So let's actually just do the first one and finish it and clean it up. And then we'll deal with the U substitution step for the other one, okay? All right, so what's the antiderivative of sine of x? Okay, so negative cosine of x. And we'll evaluate that at pi and 0. So I've got negative cosine of pi minus negative cosine of 0. Okay then, so what is the cosine of pi?
It's going to be negative.
It is -1, which then also has a negative on the outside. And then this has a negative and a negative here, so this is going to be positive. So I have plus. What's the cosine of 0? 1. So this negative here at the beginning, I've got a grand total of 2. So this is 2 plus something, right? 2 plus something. All right, you ready to use the U substitution now? Believe it or not, you know what the inside function is. It's 2x. Despite the fact that it doesn't really look like there's a product, you can see the inside function. It's 2x. So what's du? 2 dx. Well, there's a dx in the problem, but there's actually not a multiplication factor of 2 outside of cosine, is there? But that's okay. We've seen that happen. We just need to move it to the other side. So dx is equal to 1/2 du. Does that make sense? So my integral will have a 1/2 on the outside. I'm going to do an integral symbol, but I'm not going to put the 0 and the pi on there. Why? I'm turning it into u's. So this is the cosine of u and then du. The dx is being replaced with the du and the 1/2. Du at the end, 1/2 at the beginning. The 2x is getting replaced by the u. So this is 1/2. Okay, so what's the antiderivative of cosine? It's positive, actually, on this one. Sine, yeah, positive sine of u. And we don't need a plus c because we're doing definite integrals, right? They'll cancel out. So this is 1/2, but it's not really sine of u. It's supposed to be sine of 2x. And the x is being evaluated then now from pi down to 0. Okay. The 1/2's okay. We've got the sine of, well, let's plug the pi in for the x. This is 2 pi minus the sine of 2 times 0, which is 0. Sine of 2 pi is 0. Sine of 0 is 0. All that work for nothing, literally. The number 0, right? All of this is 0. So I have 2 plus 0 for a grand total of 2. Any questions?